Statistical geometry, a new way to see spacetime. What if spacetime isn't smooth at all? What if the geometry we see is only an average? A shadow of something deeper? Something statistical? In this video, I want to show you a new way to think about spacetime. A framework called statistical geometry. A bridge between general relativity and quantum field theory. The big shift. In Einstein's picture, spacetime is a single, perfect metric. A smooth fabric defined at every point. But nature doesn't behave that way. Quantum physics tells us the world fluctuates. It's noisy. It's statistical. So here's the shift. Spacetime isn't deterministic. It's statistical. At any observation scale, geometry is described by two things: a mean metric and a correlation of its fluctuations, bar G and C. This pair replaces the classical idea of a single smooth geometry. Why this changes everything. The Einstein tensor is nonlinear. So the curvature of the average metric is not the average curvature. And that leads to a modified Einstein equation. G of bar G equals 8 pi G times the quantity T plus tau of C. Here, tau of C comes entirely from geometric correlations. In other words, geometry itself produces gravity. Correlations act like an extra source. Even dark energy-like effects can emerge statistically. General relativity isn't fundamental. It's the zero correlation limit of a deeper theory. 3GR and QFT, two faces of one geometry. Now the picture becomes beautiful. When correlations fade away, spacetime becomes smooth. And that's exactly the world described by general relativity. But when correlations dominate, fluctuations take over. Physics becomes a hierarchy of expectation values and correlation functions. And that's quantum field theory. Two theories, two limits. One underlying statistical geometry. For the dynamics of correlation. To make this framework complete, correlations must evolve. So we introduce a second field equation. Calligraphic D acting on C equals calligraphic S. This is the dynamical law for geometric fluctuations. Together with the modified Einstein equation, spacetime is governed by two coupled equations. G of bar G equals 8 pi G times the quantity T plus tau of C. Calligraphic D acting on C equals calligraphic S. One equation for the mean geometry. One equation for the correlations. 5 geometry runs with scale. There's one more ingredient. The observation scale delta. Geometry depends on how closely you look. So correlations must satisfy a scale evolution equation. Delta times the partial derivative of C with respect to delta equals beta of C. This is like renormalization in quantum field theory. But here, what runs with scale is geometry itself. Spacetime becomes a flowing, scale-dependent statistical system. 6. What does the correlation look like? A key question. What form should the correlation function take? The answer is surprising. There is no single fundamental kernel. Instead, correlations are effective and depend on the scale. They must satisfy covariance, symmetry, positivity, locality, macroscopic consistency. But within those rules, many forms are possible. Gaussian kernels, power law kernels, heat kernels, green function kernels, spectral kernels. The important object isn't one kernel. It's the entire family, the set of C sub delta, a scale-dependent trajectory through geometric space. 7. The big picture. Let's step back. Geometry is statistical. GR is the infrared limit. QFT is the ultraviolet limit. Correlations have their own dynamics. Correlation kernels run with scale. Spacetime is not fixed. It flows. This framework gives us a new bridge between gravity and quantum theory. Without quantizing the metric, without discretizing spacetime, and without extra dimensions. Just geometry, but statistical. If you want to explore this new perspective on spacetime, or see how GR and QFT emerge from a single underlying structure, check out the full paper series in the description. This is Statistical Geometry, a scale-dependent, correlation-based view of spacetime.